Hello everyone, my name is Filipe Cumaro. I am a PhD candidate at the Delft University of Technology, where I've been working on robust and scalable multiscale linear solvers for highly heterogeneous formations. Numerical simulation is a very powerful tool to better understand fluid flow in porous media. But for large heterogeneous models, it can take a long time to run an entire simulation. Most of this time is spent solving large and complex systems of equations. Although the mathematical model that describes multiphase compressible flow is hyperbolic, we can focus on the pressure equation, which is elliptic, to accelerate the solution for the whole system. When it comes to elliptic problems, domain decomposition methods have long been used to enable parallel computing. Domain decomposition works by employing a divide and conquer approach that's very suitable for large parallel computers. Multiscale methods have also been used successfully for elliptic problems. They provide an accurate way to represent quantities across different scales. In this work, we employ a domain decomposition method with a multiscale step to accelerate the solution of elliptic problems. In our approach, these two methods are combined in a two-level preconditioning framework. This means that we use them to accelerate the solution of a linear system of equations. So, at a local stage, the computational domain is divided into non-overlapping subdomains. In these figures, this corresponds to the bold red lines. Each subdomain is then extended by a given number of layers of elements to form an overlapping partition. That's what's represented by the shaded regions. Next, a restriction of the global problem is solved on each overlapping subdomains. The solutions to the subproblems capture local features of the global solution. Now, this domain decomposition method can be employed as a standalone preconditioner, but it is not scalable. What this means is that as the mesh is refined and more subdomains are added to keep the size of the local problems constant, the number of steps required to solve the same problem increases. This is due to the fact that the subdomains are only able to exchange information through the overlapping regions. So any changes in the local solutions will take a number of iterations to reach all the subdomains. This can be remediated by solving a coarse global problem, and then we can reinforce scalability. In our case, we employ a fully algebraic multiscale method to assemble the coarse problem. The multiscale method provides a set of basis functions that couple the local subdomains. What's more, these functions can represent heterogeneities in the medium accurately, since they are the solution of local problems. To illustrate the capacities of our solver framework, we present three numerical examples. First, a 3D model problem in which we place high permeability contrasts at the vertices of our non-overlapping domain decomposition. We see that by adding the multiscale stage, we get a scalable solver framework, both in terms of the number of iterations and the total time to solve the problem. We also verify our approach on two 2D cases based on data from benchmarks. First, a layer of the SPE10 model and a vertical adapted slice of the Sleipner CO2 reference dataset. In both cases, the two-level approach again performs well when we compare it to just employing a domain decomposition method. So, in summary, by introducing the small scale stage, we have a solver that is both robust with respect to changes in the permeability distribution and scalable for parallel applications. Thank you very much for your attention.